Hi, I'm glad to present my work, SmoothSwap, a simple enhancement for face swapping with smoothness. This is published at CBPR this year and then accepted as oral presentation. And this is joint work with Ji-Hoon Lee and Byung-Tak Sang, and which are at Kakao Brain and Seoul National University. And this work is about making face swapping models simpler and easier to train, focusing on the smoothness of embedding. And this is a distinctive approach compared to the previous face swapping models, which often use complex architecture and loss functions for the performance. And I'll explain how we achieve this goal with simpler and easier methods. So first of all, what is face swapping? Given two images, A and B, or source and the target, as shown here, face swapping model has to create the third image, C, and C has to have the same identity as A, and except the identity, it has to be perceptually the same as B, the target. And let me show how this actually works on a real-world example.
I'm an audience making movies.
So you're given with source image.
Film. I'm an audience making movies.
And a target image actually is video.
In every possible way as a storyteller, as an artist. And there's
the identity is actually swapped with the given source image as
some
shown
days we're just sitting there
on
and
the
saying,
right.
like, I don't.
Okay. And so that was the face swapping problem. And what is the main difficulty in the face swapping? So the main difficulty here is that these two conditions are actually competing each other. So to see the loss functions, the ID loss considering the first condition is straightforward, where we use an identity embedding model to extract the identity as vectors and compute the distance to compare the identities. But the problem comes from the perceptual loss for the second condition, where we want to consider the difference between B and C while excluding anything related to the ID. But there's no good way to do so. There's no good way to exclude the identity only. So we usually resort to L2 loss or VGG19 loss, which prevents any kinds of change from B. And so, since this loss is too simple but too strong, the L2 loss or VGG19 loss, so the identity loss for the first condition is often dominated by the second loss. As a result, model can change the identity, but only minimally. So to prevent this, what we need is stable gradients, stable ID gradients, and consistent ID gradients. So, and we want the gradients to be solid enough to stand against the perceptual gradients throughout the entire training process. So the main idea to achieve this in this is my work, SmoothSwap, is to propose new identity embedding, which is trained using supervised contrastive loss. When we use contrastive loss makes the embedding space smoother, which can give stable gradient directions for the face swapping model. Because the space becomes smoother, we can get the stable gradient directions. Actually, the previous standard in face swapping was to use arc face embedding. Arc face is actually trained for face recognition, and it's kind of optimized for the face recognition, and which is a purely discriminative task. And there's a high chance that the learned embedding space can be non-smooth. So as shown in the figure, on the left pane, this can be the situation in the arc face embedding space. So you can classify the identities, but the space can be very highly non-smooth, so that the gradients cannot be defined in between the identities. But on the other hand, if we make the embedding space smoother, then we can easily get stable identity gradients. So that is the main idea. To recap the main idea, so we use contrastive loss, and if we use contrastive loss, we can retain more information in the embedding space. And with more information, we naturally get this smoother embedding space, and we can get stable gradients. And with the stable gradients, we have additional advantages, which are we can use a simpler generator architecture, simpler loss functions, and faster training. And actually, before getting into the details, I'd like to give you another perspective why smoothness matters in the embedding space. Sorry. So for many real-world data, the underlying structure of data is actually multi-manifold structure. And why? Because there are two kind of features. One is, the first is continuous features, and the second is discrete features. And the manifold structure comes from the continuously varying features as shown here. On the top, you can see the continuously varying colors, but with the same class, cup. But there are discrete features such as object class as shown here. The car is different from cup, and these are discrete. There's no intermediate class that connects a car and a cup. Yeah. And I'd like to emphasize that the phase swapping problem is not an exception. So phase swapping model also has a multi-manifold structure, and the continuous features here is the person identities. So if we randomly pick two identities, we can always imagine the intermediate or average of two identities, and we can always imagine there exists such an identity. So which means that these when we interpolate these two identities, we always have the continuous curve in between. So, and on the rest of the features are discrete. And so, but we are focusing on the identity embedding here because, so since the manifold structure is due to the smoothly varying identities, we want to make the identity embedding space itself has to be smooth enough, so that it can serve as coordinates for the manifolds. So that's another point of view from the geometric perspective. And so we trained the identity embedding with supervised contrastive loss, and we can actually, with this newly trained identity embedding, we can design a much more simpler architecture for the generative process. So in the previous models, which are shown in the second and the third, they are pretty complex and complex components such as mask-based mixing, and etc. And there are some on a hi-fi phase model also has some 3D phase modeling component as well. But in our case, which is a very simple unit architecture. And the loss functions are simple as well. And we only use 3 loss functions, but the previous models actually use 4 or 6 loss functions, which is very difficult to stabilize or balance between these loss functions. But we only use 3 loss functions, which are essential for the training. The first one is identity loss, which is for the first condition, and the second is the change loss, which is for the second condition, or perceptual loss. And the third is adversarial loss to make the generative image plausible. And this is it. This is all of our model components. And let's see some experimental results. And if we qualitatively compare our model's results with the previous models, our model shows much more active change in face shape. For example, shown in red box, we can see that the shape of the chin of the generated image faithfully follows that of source images. So the chin is kind of grown round. And quantitatively, we also achieved the state-of-the-art results for the identity-related scores. We are not as good as the previous models in perceptual scores, which is condition 2, but on overall score, we achieved the best. And also, another advantage is faster training. And since our motivation was to make this to get the stable gradient with smoother embedding space, we actually observed that the training is much more stable and fast. So as you can see here, the solid lines are the results for our model, and which converges much more faster and converges to a smaller value, actually. And qualitatively, it also converges to the correct results much more faster. And these are some of the results for the faces in the wild. So this is the target image, and this is the source image, and this, the large image is the subtle results. And without any further training, we also applied this model to the matte faces dataset, which is composed of oil paintings. But the model is never trained for this kind of data, but it actually performs quite well. And we also confirmed the smoothness of embedding, the newly trained embedding, by taking some interpolation experiments. So the leftmost and the rightmost are the actual images from the two different identities. And we interpolate these two identities in different embedding spaces. So the first row is our embedding model, and the second one and the third one is actually our face model, are different embedding space. And if we interpolate these ID1 and ID2 identities in our embedding space, the identity moves much smoother. And so this kind of confirms our hypothesis. So in conclusion, we propose SmoothSwap, and it's a simple and fast face swapping model. The main idea was to use the smooth identity embedding suited for generative task. I already explained that this part, but so the previous models always used the arc face, mostly used the arc face, which is not trained for generative task. And we argued that this is the main reason why the previous models have to use very complex components to compensate this. And SmoothSwap showed comparable or better performance with considerably simpler architecture and loss functions. And this is expected to be very useful for industrial applications because our model is much has a homogeneous structure, so it can be parallelized very easily. So, and it is also beneficial for tackling more complex problems.